Cool. Today I'm going to talk about the Rsync algorithm. But before, I want to encourage everyone to give a talk in PapersWeLove. This is my meetup profile. 3 years ago, I joined the meetup, and I wasn't very sure about giving a talk ever, as you can see there. So I encourage you to allow yourself to make mistakes and come here and talk about a paper that you like. Let's go back to. Cool, the Rsync algorithm. So before starting, I would like to know who has used the Rsync tool before? Everyone. Okay. Who still uses it? Who knew it was part of a PhD thesis? 2. And finally, raise your hand if you read chapter 3 of the PhD thesis. Cool. That's good. That means that I can go through my 145 slides. Okay, so this is Andrew Tridgell, the author of the thesis. The Rsync algorithm seems to have been first described in a 1998 technical report written by Andrew Tridgell and Paul Mackerras. It was also included later on in this thesis about efficient algorithms for sorting and synchronization. Tridgell is also known as the co-creator of Samba, and currently he spends his days prototyping pretty cool like tailwind drones or UAVs. Paul Mackerras was one of the authors of the PPP daemon, which I'm sure many of you used back in the days to connect your super fast 56K modems to internet using Linux. But most importantly for this presentation, he was one of Andrew's PhD thesis supervisors, and the person who suggested the Rsync fast signature, which was based on other 32 ideas. So what's the motivation for the Rsync algorithm? So they basically created Rsync because they were frustrated of their slow internet connections and basically high latency, low bandwidth connections. And it turns out that that's still true today. So most of the world is actually like having a really crappy internet these days. And this is Akamai's State of the Internet report, specifically from the first quarter of 2017. And it only shows download speeds. So like the orange colored countries, like Colombia, where my home country, we usually have 5 megabits per second of download speeds, and 1/5 of that bandwidth for upload speeds. So it's very frustrating every time I go to Colombia and try to get some work done. It's extremely frustrating to try to push like file updates over my mom's internet connection. So this is like the main motivation that kind of drew me to present the Rsync algorithm and to look into the details of the algorithm, because the techniques and principles that are used underneath I think are still very valid. And this is the average like connection speeds for China, Colombia, South Korea, and United States. It took China and Colombia 10 years to offer their citizens 5 megabits per second download speeds, and South Korea is beating everyone by a good margin. But like their growth, it looks kind of weird. So I don't know. I picture them like this, like a firefighter trying to control a fire hose, which is a good problem to have in terms of internet speed. And so, which brings us to the Rsync algorithm and the design goals that were defined by Andrew Tridgell in his thesis. So since you didn't read the chapter 3 of his thesis, I'm going to read over the design goals that he set out. The first one is that it should work for arbitrary data, not just text. And the total amount of transferred data should be about the size of a compressed DIV file. And it seems like back in the days, sending DIV files back and forth was something common. It should be fast for large files and large collections of files. Fourth, the algorithm should not assume any prior knowledge of the two files, but should take advantage of similarities if they exist. And the number of round trips should be kept to a minimum to minimize the effect of of course, transmission latency. And finally, the algorithm should be computationally inexpensive, if possible. So with these goals in mind, let's look at the first attempt to solve this problem. Here we have two files, A and B, located in different machines that we are calling here client and server. The files are read and written in blocks of equal size. Remember that we're talking about efficiently sending file updates to a remote location. This assumes, of course, that a full file synchronization happened beforehand. So in this example, B is a version of A at some point. And yeah, and so it always starts when A or the client wants to send a file synchronization to the server. Once the request is received, the server starts to calculate B's block signatures. And David gave an awesome introduction to hashes. And for those who still have the concept of like signatures and hashes a little bit blurry, signatures or hashes are at a fixed size value that represents an arbitrary size value. So for Rsync, we're calculating like signatures per block in this first attempt, and they are fixed sized. So the server is going to calculate signatures for all the blocks in the file, and then once the signatures are all like calculated, they are sent to the client. And so the client is going to take these blocks and is going to build a signature lookup table that is going to use to kind of start reading his block files, his blocks in the copy of the file, and it's going to start calculating this like the same signature using the same size as the server, as block size as the server, and if there is a match for that signature, the client is going to send the block index in the signature table that corresponds to the same block in the copy that server has of the file, meaning B. And the goal is to reconstruct C with pieces of A and B. So once the index makes it to the server is going to do a random file seek in file B, and it's going to take that piece of data and it's going to start reconstructing C. The client, in the meantime, is going to start also reading the next block and calculate the signature again for that block, do a lookup to see if there is a block in B that matches the same content. And this time there is not a match. So the client sends the block as is to the server. And it gets written to C. And it will keep going on and on. It will send indexes, data blocks, until C is fully constructed. This is like the general behavior of the Rsync algorithm. But in this first attempt, there's a problem. And the problem is that since we are using fixed size blocks to read and calculate the signatures, the client can only find matches at block boundaries. If one or more bytes are inserted or deleted in the file, the client will send the entire file, as no block will match. And in fact, when I started implementing the Rsync algorithm in Go, I hit the same problem because of my flaw interpretation of the algorithm. I mean, the PhD thesis is very simple to read, but once you start implementing the algorithm, you start finding these nuances that are not written down in the thesis and the key parts of the behavior of the algorithm. So the first attempt is not enough because of the blocks, the calculation of the signatures are block boundaries only. So the second attempt basically complements the first one by generating the same type of signature, a strong signature. Not only a block boundaries, but also a byte offset. And this will effectively allow the insertion and deletion of bytes at any location. However, because we're also using only one signature, like one strong signature algorithm, like in the case of Rsync, MD4 was used at the time. A block boundaries and also a byte offsets. It's very expensive computationally. At this point, no fast rolling checksum has been considered. This is bringing us to the final solution, which is using two different types of signatures. The signature algorithm, one weak and one strong, in terms of like random collision probabilities, or false positives. The weak signature has to be fast and inexpensive to calculate, therefore with high random collision probability, but low enough to be effective at quickly filtering false positives without too many collisions. It is calculated at every byte offset, and that signature algorithm is called the Rsync rolling checksum. It is based on other 32 ideas and is the contribution of Paul Mackerras to Andrew Tridgell's PhD thesis. And the second signature is called a strong signature algorithm, and that one has to have really low random collision probabilities, and so because of that, it is more expensive to calculate. And David, in the previous talk, David was mentioning it was talking mostly about cryptographic algorithms, which are very expensive to calculate for this kind of problems. But the key of the Rsync algorithm is that the signature is supposed to filter out false positives so that the strong signature is not used as often as in the second attempt. The Rsync Unix tool right now uses MD5. It started using MD4, and for some reason that I don't know, they switched to MD5. And it really doesn't need to be a cryptographic hashing algorithm. It just has to have a low random collision probability. You could use XS hash, Murmur, FMB, or any other that has low probability for random collisions. So I was told you like animals. So to better explain this, how the two signatures come into play in the algorithm, I'm gonna run through another example. Here we have two files, client A and B, and we have some variables in A. Assume that these two are currently synchronized. I mean, you can see the same animals in both. We're going to use for the example a block size of 2 bytes. The Rsync tool uses 600 bytes by default, but it actually adapts based on the file size. But for this example, is use 2 bytes. And we also have a variable called block match. This variable will tell us if there is a block in A with a high probability of existing in B. And you can also think of it as a flag to tell us how the client will move through the A file. And we also have weak and strong variables, which is the weak signature and the strong signature of the current block. And EOF, which will tell us if the client reaches the end of the file. So we're going to start by doing some local additions to A by adding a frog and a lion to the beginning of the file, and a tiger and a pig to the end. So A is different than B. If we assume that these emojis are ASCII, are encoded in ASCII, A is different than B by 4 bytes. As we saw previously, the first thing that happens when the client sends a file update request to the service that the signatures of B are going to be calculated. So we start moving B's window in blocks of 2 bytes. Calculating block signatures. The signature table is indexed by the weak signature, and it is pointing to the strong signature, and as well as the signature table is going to be indexed by the weak signature, and it's going to point to the strong signature and the block index in B. So the same is going to be done for the next block, and the next, and the next. And so once the signature table is complete, it is sent to the client. And And the client begins to read A in blocks of 2 bytes as well. It calculates the weak signature for the block because it's faster. It's trying to filter out, and it looks it up in B's signature table. And this, in this case, because it's new data, the block and the line are new. They don't match with the signature table, with any block in B that is in the signature table. So this tells the algorithm that we are going to move byte by byte instead of block. Instead of a block, rolling. And this is to identify what bytes are different from A that are not in B. So it moves a byte to the left, to the right, and it queues the previous byte so that it's going to be sent to the server. Or you can also think of it as the operation bus waiting to head to the server. And so it does again the same for this block. It calculates the weak signature. It doesn't match. It queues the lion as well because it's not in the server. And it does the same for this one. The panda and the cow, they exist in the server, so it will be a match. And it will also calculate the strong signature for these two. It is a match as well. And now our variable block match is true, and we can move by blocks. And we also queue the index of the block that was matched. So this time the turns for the cat and the mouse. It's probably not a great idea to have them together, but let's hope nothing happens. The weak signature is calculated for this too as well. Another lookup. Strong signature. Lookup. There's also a match, so the index is queued for this too. And it keeps going with the fox and koala. It's also match, queues the index, and now these two are new. And so there is not going to be a match for the weak signature calculation. And because it's also the end of the file, the two are going to be queued in the operations. And now we go to the server, and we're going to look at how C is constructed. So the operations in queuing the client are going to be sent to the server. And we're going to do it by one. In a more real scenario, they will be flushed out to the server once a buffer's size limit is reached or a timeout is also reached. So we write the frog and the lion to C. When a block index is received in the server, a random seek in B is done to find the panda and the cow. Some of you might ask why a random seek, and this is because we are transmitting over the network and operations might not arrive in the same order they were sent. So the panda and the cow are replaced. It's the same for this one. And the fox and koala. And now C is fully constructed, and it is swapped by B. Now A and B are fully synchronized. To recap, we now have a better understanding, hopefully, of how the Rsync algorithm works and how the authors organically arrived to it. We mentioned 7 main components and show how they are used to identify and send file updates. These components were the weak signature, which is the Rsync checksum, the strong signature, which could be, and the Rsync tool is MD5 right now. The block size, which is 2 bytes for the example. We also mentioned the block operation that is sent to the, from the client to the server, and a block signature, which is sent from the server to the client. And we also mentioned the signature table that the client built with the block signatures that it receives from the server. And finally, we also saw the signature search algorithm playing in the example. Now let's look in detail how the rsync rolling checksum is calculated. Sorry. Yeah. So here's the rolling checksum calculation for the one that is done at block boundaries. K is the offset within a given file. I is the relative index within a block or buffer of size L. And the modulus number is a 16-bit arbitrary number for simplicity and speed. And unlike other 32, the strength of the checksum algorithm, the checksum here is not a priority for rsync. Here's a function written in Go that implements the rolling checksum at block boundaries. So R is basically the sum of all the block values truncated to a 16-bit number. R2 is the sum of the product of all values by its relative index within the block, which makes the signature relative dependent on the relative position of the block value. And that was done because when the rolling checksum is happening and you're rolling byte by byte, they wanted to avoid having collisions when the byte that is coming out of the rolling window is the same as the byte that is coming into the window. In that case, there will be a collision, so they wanted to avoid that situation, and that's the reason why they made this R2, the second calculation, position dependent. And finally, R corresponds to the actual block signature, which is the addition between R1 and R2. And the R2 is I think it's left shifted to is an arithmetic left shift to make the final signature 32-bit integer. But just for the purposes of the presentation, I left it as a multiplication. And this is how the rolling checksum is calculated. And this is the key part of the Rsync algorithm, and the reason why it's so fast. There's 4 operations. There's 2 sums, 1 subtraction, and 1 multiplication. And it uses previously calculated R1 and R2 values. This is the coding Go for this rolling checksum. So as I mentioned before, the R1 here is, in the R1 calculation, we're taking out the outgoing value and summing the incoming value. Sorry, the incoming block value. For R2, we do the same. We remove the position-dependent calculation for the outgoing value, and we add the new R1. And this is still position-dependent. The reason we don't see the index is because this is actually L minus 0 because the byte value coming out of the window had index 0 in the previous block. So that's why it's not there. And the new index value for the incoming, the index value, the position for the incoming value is L. So let's keep going. And finally, the 32-bit rolling checksum is calculated and returned along R1 and R2. And this is for the next calculation to use. So that's as far as the calculations for the rolling checksum at block boundaries and at byte offsets. And so what's the probability of failure in the Rsync algorithm? So we use 2 signatures, the weak signature to filter out false positives, and the strong signature to really make sure that that specific block is existing in the server too. So the probability of failure is so Rsync is as strong as the strong signature algorithm that is being used, which in the case of the current implementation for Rsync is MD5, which is 128 bits, and that's a fairly high probability. There's a fairly low probability of collisions. Let's see. What could be improved about the Rsync algorithm, which is actually implemented in the Rsync tool, but it's not detailed in the thesis, is that you could also make the block size adaptive based on file size. I think the Rsync tool calculates the block size as a square root of the file size, if I'm not mistaken. And the Rsync tool also does pipelining. The pipelining, I think, is one of the key things that makes Rsync work really fast, is that only one TCP connection is open, and then all the synchronizations happen through that TCP connection, so it reduces the latency impact that a slow connection could make. And you could also optimize more by compressing the blocks or the entire transmission. So applications that you could, more applications for the Rsync algorithm or techniques that are used underneath are these are like some of them, like online data, the duplication, file forensics, incremental backup systems, efficient software updates. And for me, the main takeaway from Andrew's PhD thesis is that two-level hashing and two-level sorting are powerful techniques, especially when trying to make computationally impractical things practical. And the PhD thesis is half the Rsync algorithm, and that uses two-level hashing for speeding up file update synchronization. And the other part of the thesis is about sorting, and he also uses like two-level sorting to sort of have a basic sorting that is not fully done, and then to use a more expensive sorting to finish the job, and that makes things more practical. And I think that's everything I got tonight. Thank you. And this is some acknowledgments, and especially Andrew Tridgell, who helped me understand better his thesis. Yeah. Okay, questions?
We've got time for questions.
And beer.
Yes, I'm curious, from your looking through various implementations, that index table, is it getting stored on disk when the TCP connection closes and the entire session is over?
Yeah, so the Rsync algorithm was, in the thesis, is sort of designed for target to synchronize one file. But in the Rsync tool, since you are dealing with multiple files, I think, I could be wrong, but I think the Rsync tool uses a bigger signature table for all the files that have been synchronized in the past, and it reuses that to kind of speed up the construction of the signature table. But yes, if you implement the Rsync algorithm and you have the protocol and the communication implemented in different app, you could use this sort of variations and techniques to speed up the algorithm, like caching the signature table or things like that. Yeah.
Thank you.
Does that answer your question?
Yeah. I was just curious. I mean, yeah.
I actually so when I studied the algorithm, I implemented a library, and I also implemented a gRPC service that uses the library and uses LZ4 compression, and it does also pipelining using gRPC streams. And yes, so it's when you implement the algorithm in a library, you are free to use anything above that and to speed it up. Yeah.
Yeah, sure. Oh, yeah, question.
That's it. The LZ4 answered it. I was wondering about compressions.
Great. So did you get Rsync working with Go? Did you do the full algorithm?
Yes.
Great. So when you had the data structure with a map of the weak to the strong, let us say that some blocks will have the same weak structure and different strong hashes. So I wanted to know how the data structure would be changed to handle that.
So that's a great question. So the signature table, as I implemented it in Go, actually accounts for collisions is a map, and then the value is a dynamic array. So you should account for collisions in because the weak signature could have random collisions. So the way I do that is by chaining, doing chaining, basically a linked list or a dynamic array as a value of the hash of the key. We'll do it. Yeah.
Right. So you get back the array and then you search.
And then you have to search through the array. Yes, correct.
Thank you.
That's correct. Any other question? Okay. Nick.
Have you looked at any of the literature on computing variable-sized blocks in like the deduplication literature?
Not very deep. I know that you could also use rapid fingerprinting for replacing the rolling checksum. There's, yeah, Andrew Tridgell, when I was writing emails to him, he also mentioned that he's very sure that there's probably better rolling checksums. So he actually encouraged me to try multiple rolling checksums.
I just think you'd be interested in that.
Yes, I agree.
Thank you. How do you define block size? Because if block size is really small, this technique could be overhead, right? And let's imagine we have a good internet connection and we are using that that technique. And if block size is really small, we are gonna spend more time, right? Instead of improving. Yeah. Thank you.
Yes. So the paper is like 21 years old. So I will encourage you to test with like current, especially for your use case, to test with the file sizes that you're dealing with. Because that's true. The block size could determine how much CPU you're spending calculating the signatures. In the Rsync tool, if I'm not mistaken, they're taking the file size and calculating the square root, and that's what they make as the block size. Why, I don't really know, but that's what if you read the C code, they're doing that right now.